In earlier module of this chapter, that is in module 1 of chapter 3, we have learned about the fundamental metric tensor in a Riemannian space, which gives us the distance formula in a Riemannian space and associated tensors and vectors of the Riemannian space. Now, in our next module, that is module 2 of chapter 3, we shall learn about the concept of length of a vector or magnitude of a vector and the concept of angle between two non-null vectors. So, firstly, in section 1 of module 2, we shall define that how the length of a vector can be obtained in a Riemannian space. So, in module 2 of chapter 3, we first define the magnitude or length of vectors in a Riemannian space. If A and B are the contravariant and covariant vectors respectively, then the magnitude or length of these vectors can be defined with the help of the fundamental metric tensor Gij as follows: A square equals to Gij Ai Aj and B square is equal to Gij Bi Bj. So, as B is a covariant vector, so the inner product has been done with respect to the conjugate fundamental metric tensor G upper Ij, and A is a contravariant vector. So, its components are multiplied or inner product has been done with respect to the fundamental metric tensor Gij to obtain its length square. Now, if this Gij Ai Aj is equal to 1 or that is Gik Bi Bk is also equal to 1, then the vectors A and B are called unit vector. So, if Gij Ai Aj equals to 1, then the contravariant vector A is a unit vector, and if Gik Bi Bk equals to 1 holds, then B, the covariant vector, is a unit vector. A vector with magnitude 0 is called null vector, that is Gij Ai Aj equals to 0 and that is equal to G upper Ik Bi Bk. So, for a null vector, its magnitude or length is 0. A null vector and 0 vector, that is whose components are all 0, are different. So, for a null vector, the components may not be all 0, but for a 0 vector, the components are all 0. So, a null vector and a 0 vector are different. Let us see for this example, where we can see that the null vector and 0 vector are completely different. So, if V4 is a 4-dimensional space, with line element d square equal to minus dx1 square minus dx2 square minus dx3 square plus c square dx4 square, and it is known as Minkowski space-time of special relativity. So, the line element is expressed in this way for a Minkowski space-time. If minus 1, 0, 0, 1 by c are the components of a contravariant vector A I in this Minkowski space, and G11 equal to minus 1, G22 equals to minus 1, G33 equal to minus 1, G44 equal to c square, and other Gij's are 0 from the expression of line element, we can write the components of the contravariant vector as follows, that A1 equal to minus 1, A2 equal to 0, A3 equal to 0 and A4 equal to 1 by c. This c can be considered as the velocity of light in Minkowski space-time. So, if we calculate Gij, Ai, Aj, then we get that G11 A11 plus G22 A22, GA33 A33 plus G44 A44, and if we put the values of these G11 and Ai's, we are getting this is equal to 0. Therefore, Ai are the components of a null vector in V4, but it is not a 0 vector, as all the components of this vector is not 0. They are minus 1, 0, 0 and 1 by c. Now, let us see another example where we can see that the null vector and 0 vector are different. Suppose 1, 0, 0 and 1 by k square, k being constant, in a space with line element dx square equal to dx1 square plus dx2 square plus dx3 square minus k to the power 4 dx4 square. Now, we shall see that this is a null vector, but not a 0 vector. In this case, G11 equals to 1, G22 equals to 0, G33 equal to 0 and G44 equal to minus k to the power 4, and the components of the vector are A1 equals to 1, A2 equals to 0, A3 equals to 0, A4 equals to 1 by k square. Hence, if we calculate Gij, Ai, Aj, we are getting the value 0. So, Ai are the components of a null vector in V4. Now, let us see that the associated vectors for a Riemannian space Ai and A upper I have the same length. We have just learnt about the associated vectors in earlier module, and here we shall see that the associated vectors have the same length. So, Ai can be expressed as Gij, Ai, Aj with the help of the definition of associated vectors, and that can be written as Aj, Ai, and that is equal to Gij, Ai, Aj. So, they have the same length. Now, in section 2 of module 2 of chapter 3, we shall learn about angle between two non-null vectors in a Riemannian space. In our earlier days, we know how to calculate the angle between two vectors by the use of dot product and cross product. Analogously, here we shall find the angle between two non-null vectors in a Riemannian space in this section. So, let us see how the angle between two non-null vectors can be obtained with the help of the fundamental metric tensor. So, in section 2 of the module 2 of chapter 3, we shall learn about angle between two non-null vectors in a Riemannian space. Now, consider two directions defined by the unit vectors a I and b I at some point P. Now, since the space under consideration is now Euclidean, the cosine law following from the formula of Pythagoras gives q r square equals to p q square plus p r square minus 2 p q p r cos theta. That is, in figure we are making a triangular shape p q r, and in this triangle we know the above relation always hold, that is q r square equals to p q square plus p r square minus 2 p q p r cos theta. We can see from this figure that in this PQR triangle the above relation holds. Since AI and BI are unit vectors, QR square equals to 2 minus 2 cos theta. From the earlier figure, the components of the vector joining R with Q are AI minus BI. So, the square of the length of the vector QR can be expressed as Gij AI minus BI into AJ minus BJ. And if we just break this expression, we are getting Gij AIAJ plus Gij BIBJ minus 2 Gij AIBJ. Now, as AI and Bj are the components of unit contravariant vectors, so the value of Gij AIAJ and Gij BIBJ are equal to 1. So, this gives 1 plus 1 minus 2 Gij AIBJ, that is equal to 2 minus 2 Gij AIBJ. So, from the expression of 2 and 3, we get that the value of cos theta is coming to Gij AIBJ. So, the cos theta, that is the angle between the two non-null vectors whose components are a I and b j, can be obtained by this formula, that cos theta equals to g I j a I b j, and as they are the unit vectors, a I and b j are the unit vectors. So, we are getting the relation 4. So, for general vectors, that means they are not unit vectors, the angle theta between two contravariant vectors whose components are a I and b j can be defined as in this way: cos theta equals to g I j a I b j by root over g I j a I a j and into root over g I j b I b j. Since g I j a I b j, g I j a I a j and g I j b I b j all are invariant, so the angle between two contravariant vectors is also invariant. Now, from this expression, d square equal to g I j dx I dx j, that is the distance formula for Riemannian space. We get that the length of the displacement vector dx I 0 0 is given by root over g 1 1 dx 1, as the other components are 0. So, for the vector dx I comma 0 comma 0 is given by root over g 1 1 dx 1, and similarly for 0 dx I 0, the value of the length of the vector is root over g 2 2 dx 2, and for the vector 0 0 dx I, the length is root over g 3 3 dx 3. So, the cosines of the angles between these vectors can be obtained by the following way, that cos theta 1 2, that is dx 1 vector and dx 2 vector, can be obtained by the formula g 1 2 by root over g 1 1 g 2 2, cos theta 2 3 is equal to g 2 3 by root over g 2 2 g 3 3, and cos theta 1 3 equals to g 1 3 by root over g 1 1 g 3 3. Now, for the covariant vectors with components a I and b I, it is defined as cos theta equals to g I j, that is g upper I j here, a I b j by root over g upper I j a I a j into root over g upper I j b I b j. And if a I are the components of contravariant vector and b j are contravariant vectors and covariant vectors, then cos theta can be defined in the following way, that a I b j root over G I j A I A j into root over G upper I j B I B j. So, in the above expression, in the numerator G I j's are not coming, as A I and B j, one is contravariant vector and other is covariant vector. So, if we use the rule of associated vectors, then automatically G I j will come to the numerator. Now, two vectors are said to be orthogonal if G I j A I B j or G upper I j A I B j equals to 0. That means, theta will be the pi by 2. So, this is the condition for orthogonality of two vectors in a Riemannian space, that G I j A I B j equals to 0. Now, let us see with an example that how the angle between two non-null vectors can be calculated. Now, suppose we have the Minkowski space time with the line element given by dx square equal to minus dx1 square minus dx2 square minus dx3 square plus c square dx4 square, and the vectors have component 1 0 0 0 and root 2 0 0 root 3 by c, and they are the unit vectors, and we can find the angle between them, and we can also see that the angle between them is not real. So, let us see how we can find the angle. Now, from the expression of line element, we have G 11 equals to minus 1, G 22 equals to minus 1, G 33 equal to minus 1, G 44 equal to c square, where c is velocity of light in the Minkowski space time, and the components of vector A I is 1 0 0 0 and B I is root 2 0 0 root 3 by c. Then from the definition, as A I and B I are the unit vectors, so a square equals to 1, and the value of cos theta, if we calculate the G I j A I B j, and as the denominator the expression is 1, we can find the value of G I j A I B j, and it is coming to minus root 2. So, the angle between these two non-null vectors are not real. So, from this expression we can see that the angle between them is not real. Now, let us see another example when the components of two contravariant vectors are orthogonal unit vectors. So, if P I and Q j are orthogonal unit vectors, then the above expression G H j G I k minus G H k G I j with the product of P to the power h, P to the power j, Q to the power I, Q to the power k is equal to 1. Now, as P I and Q j are orthogonal unit vectors, so we have the relation this G I j P I P j equals to 1, G I j Q I Q j equals to 1 and G I j P I Q j equals to 0. Now, if we break the brackets, we are getting the above expression in the following way, and if we use the relations obtained in the earlier slide, we get the value is 1. So, this is the an example where the components Pi and Qj are unit orthogonal vectors. So, in module 2 of chapter 3, we have learned two things. One is the magnitude or length of vectors in a Riemannian space, and we have seen the use of the fundamental metric tensor to obtain the length of vectors. And in next section, we have obtained the angle between two non-null vectors in a Riemannian space, again with the help of the fundamental metric tensor, and seen the orthogonality condition of two non-null vectors. So, with this second module, we end this chapter.